Hello. In this exercise, we are going to go over what is known as an extended flow state. An extended flow state builds upon the equilibrium of a flow, adding different properties, different transport properties. Once again, a flow state is discussed in chapter 1, and the model that we are going to use, SL model, is discussed in chapter 3. But a detailed knowledge of that is not required to understand what we are going to do now. So we'll pick up a problem. It's a quite advanced problem in a sense. This is a pump, and we know some information about the state 1 and state 2. Notice these are called flow states. A flow is going in and flow is coming out. And essentially the purpose of a pump is to raise the pressure. So as you can understand, we are pumping the fluid, in this case water, and a shaft is doing the job. There are blades inside like this, which is churning the water around, and it goes to a place called a volute where the pressure increases when the flow slows down. Now, these are not the main part of this problem. What we are after is that if we know what's going in, the state of that flow, and state what is coming out, we can know a lot about what's going on in the pump. Actually, we can determine the shaft power. So what is given is a lot of information about state 1, inlet state, as you can see, and a lot of information is given about exit state. So what we are going to do, we are going to launch a flow state test app using SL model. Just a quick note here that I would suggest that for the system state SL model, you go over this video first, how to find a system state, before you solve this particular flow state problem. So this is how we're going to build up one video on top of another. So we have already chosen what is called a flow state branch. And the particular model we are after right now is SL model, because liquid water can be modeled by SL model. And this is exactly where this particular video is going to be. So we launch the test tab by clicking this tab. Again, you can go back and forth between, say, discussion and here. If you face a problem, just post a question and you will soon get an answer. Okay, so the state panel is displayed here. Again, a state is a collection of different properties, but unlike the system state, you will see that some of the properties are different here. For instance, m dot appears, vol dot, volume flow rate. As you put the pointer over, it explains the formula for volume flow rate, formula for mass flow rate, etc. So these are the properties of flow. However, the underlying equilibrium, the blue properties, PT, VUHS, etc., you will see that they are the same group of properties that you encounter in a system state or a flow state. So a flow state kind of builds over this core thermodynamic equilibrium. Okay, so let's start with the problem at hand. Liquid water is already selected. So let's keep entering the properties we know. Pressure is given. Inlet pressure is 100 kPa. Temperature is 30 degrees Celsius. Velocity is 10 meter per second. And the area is given. Area is not given. In fact, the diameter is given as 10 centimeter. So we can enter an equation here. We can say equals pi times diameter is 0.1 meter to the power 2 divided by 4. Whenever you enter an equation, it must be in SI units, unfortunately. So that's our area. And if we calculate, I think that's all the information that is given. So all the other variables, a lot of other variables are found. Okay, for state 2, what is known is the pressure is given as 5,000 kPa, temperature is given as 30.2, velocity is given as 15. I've already typed that in, that's why it looks so fast. And z is 5 meter per second. Also, we know that m dot 2 equals m dot 1. Now if you do a calculate, we should be able to find the state. And then we go to the I/O panel. Let's clear this I/O panel. And we can figure out the change in flow energy without variable. You can write just an equal sign if you just want to find the amount. M dot 1 star J2 minus J1, J being the specific flow energy. And so the amount we get is 459, as you can see right here. So many kilowatt would be the answer. In other words, really, that's the increase in the flow energy of the flow. And why do you think the flow energy is increasing? Of course, the shaft is pouring in energy into the system. So this must be equal to the shaft work. But for that, we have to learn how to analyze energy equation, which we'll do later. But just from the state perspective, a flow state perspective, it tells us exactly how much is the increase in the flow energy. How much of that is because of, let's say the question was, what is the contribution of, say, the velocity? So we set velocity to 0 and, oh sorry, not 0, there is no change in velocity, so we can set velocity equal vel1 and calculate the state. Go back to the I/O panel, and now if you calculate, you'll notice that the amount has only slightly changed, 454 from 459. Percent wise, it's almost nothing. So the kinetic energy has very little contribution. Well, suppose there was no change in elevation, that Z2 equals Z1, then you come back, and if you do a calculate again, you will see it's barely changed. And finally, if you make even the temperature, suppose there is no friction, then it is possible that the temperature will also not change between the inlet and exit. If you do a calculate, I/O panel, and calculate again, you see 384 is the change in energy. In other words, because of pressure change, that's how much energy is put in. Whereas the temperature change and velocity change, and temperature change is kind of significant, but velocity and elevation change are almost negligible. So therefore, you will find it's almost a routine thing that in a flow system, in a device where there's flow going in, flow coming out, kinetic energy and potential energy are kind of neglected. The changes in them are neglected. So we'll stop here, and we'll tackle more advanced problem in a future exercise.